Good morning, good afternoon, and good evening. It depends on which region you are in part of the world. So we have people from France, we have people from China, we have people from India as well. So welcome everyone. Welcome to the Prodigy webinar series. The topic for today is M PHY-UniPro and UFS 4.0 overview, protocol analysis. And so just to tell you, the overall session is going to be for 1 hour, and first 45 minutes, 45 to 50 minutes is the presentation, and the last 10 minutes where we can go in for a Q&A. And this session is going to be completely recorded, and what we're going to do is we're going to send the recorded session later on to each one of you who have registered. So in case you're having some internet issues, or there's something you miss out if you've joined in a little late, don't have to worry about that, right? So to present this topic, I've got two speakers here. First is Godfree Coelho. He's the founder and CEO of Prodigy Technovations. He's got a lot of experience in the test and measurement domain. He worked with Tektronix, HP Agilent, and he's been in the test and measurement. He's got deep expertise in test and measurement domain, and he went on to found Prodigy Technovations, right? And from the last 10 years, he's been running Prodigy Technovations, and Prodigy has been, delivering products which have been used by most of the semiconductor companies across the world, right? So that's about Godfree Coelho, and with him will be Vibhav. Vibhav has got more than 13 years experience, deep expertise in system and software development, and he's involved in architecture and implementation of various high-speed protocols, and he's been with Prodigy for almost like close to 7 years now. So with this, what I'll do is I'll hand over the session to Godfrey and Vibhav. So Godfrey, you can take it over from here, and I'll come back around 45 to 50 minutes, and we'll have the Q&A, and I'll help you with that.
Okay, thank you, Asif. That was a nice, kind introduction. So I'm not going to spend much time on again. Let me move to the next slide. So the agenda for the meeting is we'll give a brief overview of Prodigy. Like some of you may be very new to Prodigy Technovation, but we have been doing webinar for last 1 year. Some of you might have attended. Bear with us for a couple of slides because it may be a same repetition for some of you, but those who don't know, it may be we would like to give some introduction. Then we talk about M5 specification overview, UniPro protocol layer, and UFS 4.0. And the most important part of the presentation is the challenges of UFS 4.0 protocol analysis. Like currently, most of you are using UFS 3.0 or UFS 2.1. But very soon this technology will move to UFS 4.0. This webinar would help you to plan yourself and think about what are the different challenges you may come across while doing the UFS 4.0 protocol analysis. And then we just give a couple of slides on what our product is all about. Okay, next slide. So about Prodigy, we are based in Bangalore. It's kind of a Silicon Valley of India. So most of the semiconductor companies are based in Bangalore. So we founded this company in 2009, developing protocol decoding software for Tektronix oscilloscope. We are a technology partners for Tektronix, and over the period of time, customers came back and said they need more capability. So we developed our first eMMC protocol analyzer in year 2015. That product has been very well received by the customer. We have sold hundreds of units to different customers, and we still get requests for those products. Currently, we are a team of 40 to 45 people based out of Bangalore. Most of them are in research and development, in hardware design, which includes board design and RTL, software development. And my colleague Vibhav Karki, who is presenting, is leading the software team here. And then we have two vertical business. One is a product development team, and then we also distribute some products. Most key part is we keep track of different technologies and what is going on in the industry. So we are a contributing member of MPHY Alliance, and we are a member of JDEC, SD Association, PCIe, SIG, Open Alliance. Open Alliance deals with the automotive Ethernet. So we continuously actively participate in MIPI Alliance working groups. We are very closely monitoring the changes coming up in M PHY 5.0, UniPro 2.0, so that any changes which can be supported by our product. So we will be ready to provide you a solution, whatever changes coming up in this upcoming specification. We are aware of those changes at this point of time, but we may not be able to talk about it because it's not in a public domain. Next slide. So who are our customers? Like as Asif mentioned, we have semicon companies from the top 10 semicon companies, Intel, NXP, Micron, Qualcomm, Sony, Siemens, Samsung. So though they are located at different geographies, we are able to serve them and provide a very high level of support. One of the key differentiator of Prodigy Technovation is that we are very agile and we can provide you a support within a very short notice period of time, so that you can solve your complex problems without much difficulties. Next slide. So yeah, Vibhav, can you take over from here? Yeah.
Yeah, hello. Thank you, Godfrey. Okay, so hello, everybody. So this is Vibhav Karki. I will now go through a little bit about the M PHY-UniPro and the UFS layer stack. So starting with the M PHY data rates, as you know, the M PHY operates in two speed modes. One is the low speed data rate, wherein it operates in the PWM encoding, and another one is the high speed data rates, the NRZ encoding. So in the high speed, you have both the rate A and rate B. Similarly, you have both in rate A and rate B, even in the PWM. Now, in the high speed, currently until UFS 3.1, it was HSG4, which was rate B 11.6 Gbps was the highest. But recently with UFS 4.0, you have the HSG5 gear, which can operate up to 23.2 Gbps. Now, when you come to the low speed data rates, you have from PWM G0 to G7, but in the UniPro doesn't use the PWM G0. It mainly uses the G1 low speed gear. Okay, that's about the M PHY data rate. So this is how you typically connect to analyze the signals for protocol analysis capture. You can see that there's a device A and B, wherein the TX is connected to the RX and similar vice versa. So this is a two-lane device connection. Okay, this is the common burst state in a M PHY state. So as we had previously discussed, there are two speed. One is the low speed mode and the high speed mode. So the different N signal in the low speed starts with the sleep state, while in high speed it starts with the stall state. Next, you have the prepare stage, which is a diff P mode. Then you have sync and marker 0, and after that it's followed by the data can be fillers, marker 0, and other 8B and 10B encoded signals. So this is the basic operation of M PHY burst. Okay, now let's just start with the high-speed burst. So as shown previously, the high-speed burst starts with the stall state, then you have a prepare state, which is the diff P, and then you have a specific number of sync signals as decided by the host and device, followed by the start of bursts, and then the DL data packets. As can be seen, the DL data packets can be transmitted continuously, or you do have fillers in between, so that for lane synchronization and other activities. So there's also the PACP packet, which is the power mode packets, which are very essential in exchanging the gear information and other attributes between the host and the device. So the burst is ended by sending a end of burst pattern and then again it goes into the low speed, low activity, the stall state. Okay, now coming to some of the states that were described previously. Now, so as described, the stall state, it is a power saving state, which is seen in the high speed mode, that's from HSG1 to G5. Now, a similar state in the power staying state in the low speed mode will be the sleep state. So the sleep state is usually seen in all the modes. Now, coming to the hibernate. So the hibernate is actually also a power saving state. It is enabled when there's a prolonged period of inactivity between the host and the device. So this ensures that there's not much power consumed, and an in-band request can be sent to come out of the hibernate state. Okay, the disabled state is a module operation where it's disabled by the reset signal sent. Okay, now coming to all the protocol layers in the UFS. So the UFS, it occupies the highest stack. It's in the application layer. So you have a typical OSI reference model here, where you have the physical layer, then the data link, network, transport, and session. So the UniPro occupies all the contains the L2, L3, and L4 frames. So that is where the UniPro layer comes in, and in the file layer you have the uh, typical phi transaction. So you can see here, and above the Unipro layer, the application layer will be the UFS layer. Okay, one of the packets that was told previously was the PACP packets. So the PACP packets are the most important packets in the transactions of the UniPro and the UFS. So this is required because it exchanges critical information between the host and the device. So you have several PACP packets. So each of them are differentiated by a function ID. So let's briefly go through all of them. The first one is the power request. So it's sent by the host to the device for power mode change request. So similarly, you have a power confirm, which is sent the reverse direction for a confirmation that the power mode change has been accepted. Then you have the PACP capability packet, which sends the capability information, PACP EPR. Then the PACP test mode is usually used for the 5 testing modes. Then the get request, there's a PACP get request and a get confirm packets. Here, the host or the device requests for a particular attribute, and the attribute value is sent in the PACP get confirmation packet. Now, if you want to write a attribute, it's a PACP set request. A PACP set request sets the value of a attribute, and the set confirm returns the result of the setting the attribute, whether it was set or not. Then you have the PACP test data 0 to 3. These are nothing but to send test pattern for 5 testing with different PRBs, and you have different payloads in them. Okay, now coming to the DL data and the control frames. So the DL data, that's the L2 layer frames, that's in the UniPro layer, the L2 layer frames. So there are both data frames and the control frames. Now first going to the L2 data frames. So you have two traffic class 0 and traffic class 1. Similarly, in the control frames also you have the acknowledgement for a data frame or a NAC frame, which is sent from either the host or device if there is any error. So similar to the data frames, you both the acknowledged frames have a traffic class 0 and the traffic class 1 AFC. Okay, now coming to the application layer, that's the UFS protocol layer. So the UFS protocol is the consists of UPIU units that's travel between the devices on top of the UniPro layer. All of them consists of a basic header which has a fixed size of 32 bytes, and after that it contains transaction specific fields based on each of the UPIU transaction. Okay, now these are all the UPIU transactions of the UFS layer that have been listed. So the first coming to the NOP out. The NOP out is usually it's the starting of the wherein it acts as a ping from the initiated to a target. It can be used to check for whether the path between the device and the LUN is proper. The NOP-in transaction is the target response to an initiator, that's the NOP out sent. So the NOP-in is the target response for the NOP-in request. So the command transaction originates from the host and then reaches the target device. So based on what the command that has been sent, the device responds back with the particular transactions. So there are several commands like read, write, synchronize, cache, and other ones. So we will not go into detail of them, but let's go to the other UPIU transactions. So the response transaction originates in the target and is sent back to the host. So the response is in response to a command sent by the host. It gives the response whether the status, whether the command implementation has been proper or other any error status has been detected. Now, next is the data out transaction. So the data out transaction originates in the host and is used to send data from the initiator to the target device. So the target in the data, that is whenever you're doing a write command, you're sending the data out transaction wherein the data is sent from the host to the target device. Now the data in a transaction is the reverse of the data out, where it's used in the read command. So in this case, it is used to send data from the device to the initiator, that is the host. Now coming to the next, the task management request. This transaction actually carries the SCSI architecture model task management function request originating at the initiator and then terminating at the target. The standard functions are defined by the uh, SAM5 specification. So that is, you can go to it in detail in the SCSI specification. Now the task management response is similar to, it's a response for all the task management function requests that has been sent originally, and this originates in the target. Now ready to transfer. Now the ready to transfer is observed in case of the write command for the UFS protocol. So the target device will send a ready to transfer transaction when it is ready to receive data from the host. So it allocates all the buffer space and other parameters, and so that the target can send so that the target can receive all the data from the host. Now next, going to the query request. Now the query request originates in the initiator and used to request the descriptor data from the target. This transaction is outside of the command and task manager functions, and it's only defined only for the UFS. The query request and query response, it does not go to the SCSI. It's only defined exclusively by the UFS. Now the query response is the response for the query request transaction. It actually originates in the target and provides the requested information, whatever information was requested by the query request. The specific request descriptor information is provided to the initiator in response to the query request. Okay,
Okay, yeah. Thank you, Vibhav. So let me talk about UFS 4.0 protocol analysis. Suppose we want to analyze UFS 4, and this is also applicable for UFS 3.0 or 3.1. There are three critical steps involved in making this protocol analysis. First, connecting the protocol analyzer to the DUT, the DAT, okay, the device under test. What are the different issues are at that point of time? And then acquiring the low speed and high speed data, because we talked about the UFS technology works at a PWM speed, that is a gear 1, which is actually can be at 3 megabits per second, and it can go up to all the way to 23.2 gigabits per second. So it has its own challenges in acquiring that data. So what are those challenges we'll see, and also the solution. And then we look at the analyzing this acquired data for different protocol issues, how easily one can find problems in the acquired data. So these are the three key points we will see in this next few slides. So if I look at the MPHY signal, right, just to give you an idea, the MPHY signal is coupled with the DC coupling. If you look at most of the high-speed signals, if you look at PCIe or a USB, they always couple between the host and device using a AC coupling. But whereas M PHY being a low power technology, it is used in all these mobile devices. So they do a coupling using DC coupling, and it has a common mode voltage of 300 millivolts in the common mode at the M PHY layer. And there is a prepare state of the burst, which is something looks very similar to a burst, okay? Pulse, actually. It looks like a pulse, and then immediately followed by high speed sync symbols. So how do we accurately monitor that prepare state along with a very high speed signal? Then the signal amplitude is quite low. As per M PHY specification, it can go from 70 millivolts to 350 millivolt. Typically, what we have observed, most of the DUT support is around 200 millivolt to 250 millivolt signals. Now, the next one of the most important is that when you want to do a protocol analysis, this signal is really not compatible with the FPGA transceiver. Okay, if you really want to do a protocol analysis using the FPGA transceiver, it cannot accept 300 millivolt common mode voltage, and it becomes very challenging to do a protocol analysis. Then we have these are interfaces in the M PHY, right? They are very embedded in nature. Like there is no connector most of the time between the host and device. There is a trace which goes from the host to TX to the device RX on a PCB. Now, how do we access these signals? How do we tap into those signals? Is a very, very challenging task. And then you have a development cycles, right? You have a pre-silicon development and post-silicon development. So you use different test platforms to do the development activities. They bring in their own challenges. So these are the key information about the M PHY signals. Next slide. So what we see here in this slide, how do we address and make the signals compatible with the FPGA transceiver? So what you see here is that we have a 250 millivolt signal with the prepare state, which is something similar to a pulse, which is then followed by a sync symbols, which are very high speed switching signals, then the data followed by that. This has around 250 millivolt. It's quite a low amplitude signal with a common mode voltage of 300 millivolts. So when this signal goes through the PCB trace, and this amplitude can still drop, and the common mode voltage, if you see, it is not compatible with the FPGA. So Prodigy has developed a very unique solution, which is a active solder down probe tips, which has a signal conditioning circuit and a driver circuit. And then you have a FPGA hardware, and combining all these things, we drive the signal to a higher amplitude so that the signal can be transmitted from the test point to the UFS protocol analyzer with the expected losses, so that the signal is still can be received without much problems. And also then the noise which is getting coupled during the probing needs to be removed, and we use a signal conditioning inside the active probe so that the noise can be removed, and also make sure that common mode voltage which is good enough for the FPGA transceiver so to receive and analyze it. So that's how we actually do the probing of the signal. Next slide. So how do we access the real signal on the DUT, right? So where do you put the test points, and how do we what could be the size of the test point? So this is a very, very important information while probing the embedded DUTs. So we have a host. It may be an application processor from any vendor. It gets connected to the device. Yeah, that's maybe a UFS 3.0 or a UFS 4.0. So we recommend the test point closer to the device area. And you can see here, there are white dots. These represent the test pads. So we really request you to provide the test pads closer to these signals, so that the test pad for ground, signal, ground, signal, ground. And it is also important to decide the size of the test pad, because it can absorb external noise, or it can degrade the overall signal. So it has to be in the steps of hundreds of micron. And so for more details, whenever you are doing these test platforms, please contact Prodigy Technovation. We can really work with you in addressing these requirements. So what is recommended paths are is that ground, signal, ground, signal, ground. Okay, and the grounds has to be closer to the test point, and they needs to be connected to the soldered down probes so that we can decouple the noise during while accessing these signals. Next slide. So the another level of test platform is that like you have a FPGA based development platforms. These are commonly used for UFS controller development and debugging. This is a platform continuously maintained for debugging purpose. So if you, what you see here is that a FPGA based development boards, this could be from any of those large 3 EDA companies, or it can be from a custom design for your requirement. So these boards you can you are connecting to a M PHY 4.0 or 5.0 test chip, and output and input of this M PHY test chips are connected to another development platform. It could be another development platform, or it could be an actual UFS device board through a mini SMP coaxial cables. Okay, now the M PHY test chip is connected to the FPGA development board using the RMMI interface. And so here the challenge here is that there is no path available for us to tap the signals if you really look at it, right? So the SMP output of M PHY test chip is connected to the device through another mini SMP connector through a coax cable. So how do we connect protocol analyzer in this situation? Next slide. So what we are proposing or we are providing is a power divider interposer board. Okay, so this board will take the TX and signals from the host as well as from the device, and it will split the signal and take a portion of the TX signal from the host and device to a protocol analyzer. So this is a power divider interposer board, where this will have a mini SMP connectors or SMPM connectors, where you can connect these cables between the SMP and then take those signals to a Prodigy UFS 3.0 or a 4.0 protocol analyzer. So this simplifies your probing. This is almost like a contactless probing. So you just plug in the cables and to the protocol analyzer, and you really no need to solder the probe tips to the device under test, and you can really access those signals for a protocol analysis. Now we have a similar solution, like if you have a test point which is a mini SMP or a SMPM connector on your development board, and you really want to hook up the probes to that. So we will provide a solder down probe tips. Instead of solder down, they will have a mini SMP connector. It will directly mate with the SMPM connector on the device under test. So we do have a solution for those kind of test platforms. Next slide, please. Now coming to the most challenging task many times is that the final products, right? When you have a final engineering product or a field written product, which you want to debug and understand what's going on, that makes it very complex, because most of the time in the mobile phones and or the finished products, it's extremely difficult to tap the M PHY signals. So one of the solutions what we are proposing is that you can use the raised PCB interposers. Okay, these interposers you can see here in this slide can be raised by 1.2 millimeter or maybe slightly more, and then there is a PCB on top of it. So you can directly solder this interposer to the UFS device BGA pins, and then you can solder, or you can also maybe place it on a socket on the top of the UFS interposer board, and then you'll be able to access the signals of M PHY. You can make a provision similar to what I talked about, ground signal, ground signal, ground kind of provision to access the M PHY signals. Otherwise, you can also contact Prodigy Technovation. We can provide you a solution which can interposer boards. You can solder them to the UFS device socket, and then you can take the signal directly to the protocol analyzer. So this is another probing methodology can be used. So overall, we have a multiple solutions depending on the complexities of the device and access to the test signals. Hopefully, it will serve most of the requirements in the marketplace. So our probe tip, typical UFS 3.x probe tips looks like this. We have a long lead wire, which is a differential wire, which has a very high bandwidth. You can solder these points to the test points and access the signal. Okay, so this is for UFS 3.0. Something similar to that probe tip is also available for UFS 4.0, which has a bandwidth of 28 gigabits per second with a built-in equalizer. So on the UFS 3.0, we have a probe tips with equalizer and without equalizer. We provide both these probe tips as a standard accessory with the protocol analyzer. Depending on the customer's need, they can use either equalizer or without equalizer probe tips. But whereas in UFS 4.0, which is really very high speed, running at 23.2 gigabits per second, we strongly recommend having an equalizer on the probe tip. So if you have any questions about the probing, please contact Prodigy Technovation. Please note that probing is very important. If we do not probe the signals properly, we do not get proper output. It's like saying that garbage input, garbage output. So it is better we address this requirement carefully and systematically so that the next steps are very, we can do it without much challenges. Next slide. So currently we are shipping probe tips, you can see here in this device. So we have these high performance probe tips, which has a proper signal ground and NNP connections. On here you can see how we have soldered the probe tip to the device under test. And they are powered by a power module, which is from the protocol analyzer. All these probe tips are powered from the protocol analyzer. You don't need to have an external power supply or anything. So just hook up to the power module, it will be like powered. And the output of these probe tips is available at the mini SMP connector. This output is connected to the protocol analyzer using a coax cable, which is a 40 gigahertz in bandwidth. All right. So next step, I request to Vibhav to take over from here.
Yeah, thank you, Godfrey. Okay, so previously I had given a brief overview of both the UniPro and the UFS packets. So now let me just explain how the Prodigy Protocol Analyzer with its advanced hardware and software capabilities helps in acquiring these both UFS and UniPro packets, and also analysis of the packets, and also detection of any error on the line, which is helpful to the user. Okay, now coming to the acquiring of the low and high speed data. So the UFS 3.0 and 4.0 is actually a burst communication, and each burst is at a different speed depending on the speed exchange between the host and the device. There's also the feature to dynamically switch between rate A and rate B. That's the data rates that was we had previously discussed. So the Prodigy protocol analyzer should be able to even dynamically log to the data rate change. You even have the feature to capture data at any specific event. Now, the protocol analyzer can be used to capture data for a very long duration. There are features such as the circular buffer so that the user can retain only the most recent captured data. Then you also have now, as you know, the UFS packets and the UniPro packets at higher data rates contains a lot of data. So feature option has been given to drop any unwanted data and only capture specific packets. Okay, now let's talk about how the protocol analyzer locks onto the M5 data, that's the burst of data. As previously we had gone through, any burst starts with the prepare, that's a diff-p state, and then you have a specific number of sync symbols. Though the FPGA transceiver can use these sync symbols to lock onto the clock and then detect the data symbols. So the Prodigy protocol analyzer has two modes to identify the speed data rate. One is it uses the sync symbols to lock on to the data rate. That is one of the method. The other option that has been provided in the protocol analyzer is to lock on to the data rate depending on the PACP information. As we had seen previously, the power request and the confirm packets exchanges the data rate information in it. So this can be used to lock on to the gear that has been used in the burst. Now, auto setting of the equalizer in the FPGA is done, which so that you need not change any of the parameters, and it automatically locks on to the data. As explained previously, the Prodigy protocol analyzer also enables to dynamically switch between both rate A and rate B. Okay, now coming to the detailed part in the software. So how to acquire data at any specific event. So we have very powerful trigger capabilities, which helps the user to trigger at all the layers, whether it's at the UFS, UniPro, or at the M5 layer. You can trigger it on many of the M5, like you want to trigger on any control symbols or a particular data symbols, or any of the N5 state. So all options have been given to trigger on particular M5 at the M5 layer. Then going to the UniPro layer, you can trigger on any of the UniPro packet like a PSCP packets, a AFC, or at the start of a burst. So all this at the UniPro packets, the trigger has been given. So you have trigger options which covers the M5, UniPro, and also the UFS layer. So now next, coming to the detailed trigger, now if you want, you can even trigger on the particular parameter in a packet. So now let's take the example of a PACP packet. So now if you are using a PACP power request, it exchanges information of the mode, the TX mode, the RX mode, then the number of lanes that the host and device are operating, and also the gay information. So let's say you want to trigger on a particular gay. So even this feature has been given in the Prodigy protocol analyzer, so that you can choose on which gear the trigger has to be set. So the advanced trigger is a very powerful feature where the each of the parameter can be used to trigger. Now coming to the UFS layer, now the UFS, it's similar to the UniPro layer. The UFS packets can be triggered along with not only on any particular packet, but even on the packet information. So the advanced trigger changes as per the packet that has been selected. So all the as per the UFS specification, whichever packet has been selected, the any of the parameter on the UFS packet can be triggered on. So now if you are taking any read and write transaction, you can trigger on a particular transfer length or on a particular LBA value. So similarly, on any of the UPIU transactions, you can trigger or by setting on all the parameters. So that was about the trigger features in the Prodigy protocol analyzer, so which allows you to trigger on at the packet level and also in depth the packet parameter level. Now next, going to the data acquisition using the Prodigy protocol analyzer. So the Prodigy protocol analyzer allows you to acquire data in two modes. One, in the live acquisition mode, wherein you are continuously acquiring data and also parallelly decoding the acquired data simultaneously. And second is the post acquisition mode, wherein you can choose to only first acquire the data and then decode the data on completion of the entire acquisition. There are hardware filters which enable you to store, which enables you to remove unwanted data packets along with sync and fillers without losing any of the timestamp info. That's the timestamping between any two packets. Now you have the hardware circular buffer, which allows you the user to only acquire a specific amount of data, recent data before the stop of the acquisition. So flexibility has been given to select the buffer size. So now let's say you can choose the circular buffer. Once you have chosen a circular buffer and you choose a capture bandwidth of 1 GB. So the Prodigy protocol analyzer captures only the last 1 GB of data during the entire acquisition and filters out the remaining data. So this will help in easier analysis of the captured data. Next, you even have the flexibility in the post capture. In the post capture, which involves the software, you even have the flexibility to decode only vertical amount of the capture. Now, let us say you have captured a duration or like a data of 1 MB to 1 GB. Now, if the user does not want to decode the entire data, then flexibility has been given the protocol analyzer to choose the amount of data, whether you can decode from only 100 MB to 200 MB of the data. This is one of the powerful features that is available in the Prodigy protocol analyzer. Now in the filters, you can either filter out now, as you know, there are multiple AFC sent with different credit value for a particular DL data transaction. So you can filter out the AFCs since it is just a large amount of data. So you can filter out the AFCs using the Prodigy protocol analyzer. The second hardware filter is the DL data payload drop. Now, as we had observed previously, the basic UPIU transaction is the first 32 bytes header, and afterwards the transaction fields. So in this case, the Prodigy protocol analyzer only captures the first 64 bytes of the DL data packet and ignores the other unwanted data bytes. So with this, you can capture a large amount of data. So as I had previously in my previous slide mentioned about the AFC filter, you can see here that one DL data with a frame sequence of 10 receives multiple AFC packets with the same frame sequence of 10 with different credit value. So if you have enabled the AFC filter, then for a particular DL data with let's say you have a DL data with a frame sequence of 7, then you receive only one AFC packet is captured for acknowledge packet is captured for that respective frame sequence. So the other AFC packets which have no meaning except for the credit value change is ignored by the Prodigy protocol analyzer. Using this, you can extend your capture duration for a very long time. Okay, now going to the analysis of the UFS 4 data or UFS 3.1 data. So now you can see that the Prodigy, as previously explained, the Prodigy protocol analyzer can be used to even capture the latest UFS 4.0 package. So this is a capture from a real world DUT at operating at HSG5B protocol. So you can see that the Prodigy protocol analyzer has been successfully able to capture packets at a high speed rate of HSG5B, which is a 23.2 Gbps at both the lanes successfully. So now coming to the different views that are available in the Prodigy software. So you have all the three layers can be viewed simultaneously using the Prodigy protocol analyzer software. Now you can view the UniPro layer packets, the UFS layer packets, the correlation between the UFS and the UniPro layer, the detailed packet information at both the UniPro layer and the UFS layer, and also the data and the control symbols, that's the MPHY symbol. So you have multiple views, and these all views are configurable depending on the user. So the user can choose which view to choose, and then he can observe the packet information. At the click of a button, the detailed packet information can be viewed on different screens. Now coming to the PACP, you have we have the Prodigy software has a separate view for the PACP packets. So the PACP packets are one of the most important packets in the UniPro layer, so which exchanges in transaction information. So a separate view which captures only the PACP packets has been allowed in the Prodigy protocol analyzer. So on the all the PACP packets and their respective information of the detailed information whichever can be chosen and viewed on a PACP view. The PACP view for packet view can be linked to the UniPro layer at the click of a button. So you can easily debug all the gear change information, or when the duty has gone into hibernate, the exit of hibernate, and other line reset, lane change, speed change, all this information can be viewed at one go in the PACP view. And you can click on any of the PACP packet to link it to the timestamped information in the UniPro layer to see the exact other UniPro packet informations. So along with the packet display and analysis, there are powerful filter and search capabilities given in the Prodigy software. So you have the option to search on packets, to filter out or filter in multiple packets. Even you can choose whether to filter out only the host packets, device, or both. So you can filter out to any packets that are not of any interest, or similarly filter in only the required packets. So this is the filter in capability. So if you want to just filter in or let's say for example you want to filter only the read transactions, then you can choose to filter in only the read command and ignore all the other commands and UPIU transactions. So only the filtered packets are retained on the grid, so for the analysis of the user. So after the Prodigy protocol analyzer, along with the live acquisition, displays the statistics and analytics, which is updated simultaneously in a continuous manner. So it shows the statistics of each of the packet. That's the count of each of the packets that has been captured in both the UniPro as well as the UFS layer, where at both the host and the device levels. So it gives, let's say you have run an Android bench of 6 GB data capture. You can get to know how many of the DL data packets, along with the acknowledgements for the DL data packets, has been captured. All along with the packets, even the events like a CRC error, CRC errors, line reset, hibernate, and also PA initialization. All these events are also displayed in real time in the software. So the events and the packets captured are updated continuously at a regular interval to get the statistics. So it's the errors that are observed are also updated simultaneously. The errors, by errors you mean any of the commands have not received their response. So a command response mismatch has been observed. Now, as you know, there's a DL data. DL data packets are in order of the frame sequence number. Now, any of the DL data packets are out of synchronization with the previous frame sequence number. Even this error is reported in the Prodigy protocol software. So all the errors along with the statistics are displayed simultaneously on the software. Now, the other important feature in the Prodigy software is the correlation between the UFS, UniPro, and the M PHY layer. So you can easily correlate from the UFS view to the UniPro view. Now, let us suppose you have you want to observe a UFS transaction. Once you click on a UFS transaction, the respective DL data packet in the UniPro layer is selected. And when you click on a DL data packet at the UniPro layer, the respective symbols at the M PHY levels, either the host or device, are highlighted. So you have an easy correlation from the UFS to the UniPro to the M PHY levels. The software also has the vice versa. That is, you can auto correlate from the UniPro layer to the UFS layer. Let us say you have a DL data packet. You want to know this DL data packet corresponds to which UFS transaction. You can just right click on the DL data packet and ask it to link it to the UFS transaction, and that is that is also covered. Now, the Prodigy protocol software also has advanced search and filter analysis, filter feature, and also the analysis. The search and filter allows you to search and filter on not only at the packet layer, but also at the packet parameter level. You can even filter out or search on the parameter level for each packet. So this helps in comprehensive of the error analysis and error analysis, which helps the user to track down the errors easily. Okay, now as I mentioned, there are different views in the Prodigy software. So you can even view this, take these views and view it on multiple screens so that the linking between the UFS, UniPro, the M5 level is easily correlated. Okay, I think the next
Yeah,
slide.
yeah, thank you, Vibhav. So this is a summary of Prodigy UFS protocol analyzer. So we will support MPHY 3.0, 4.0, and 5.0. Currently, 5.0 specs are not publicly announced, but we are being a MPHY Alliance member. We are working closely, and Prodigy UFS 4.0 protocol analyzer would be completely compatible with the MPHY 5.0. Similarly, UniPro 2.0, which is also work in progress, and it will be supporting that. And UFS 4.0, it is already 23.2 gigabits. Prodigy is already supporting that. We have tested it on a live DVD. So, and these are the key features, like continuous streaming is also available. We'll have a deep buffer also will be available on UFS 4.0 protocol analyzer. We will have a soldered down probe tips with the mini SMP connectors, power divider circuit, and raised interposer boards. So to address different challenges of probing the UFS devices, we will be supporting that. And it will be quite a portable device, and it will be easily carried to the field and also field upgradable. So you can, and we are shipping UFS 4.0 protocol and analyzer at this point of time. And you can buy UFS 4 with the UFS 3 IP, or you can directly buy UFS 4.0 protocol analyzer. A typical setup of the test platform is shown here. We have a Snapdragon DUT, which has a Qualcomm SoC and a device from another vendor. And we are probing those signals using soldered down probe tips, and then connecting to the protocol analyzer using mini SMP cables, and then analyzing the data. This is just to give you a typical idea how does the entire test setup would look like. So here is our contact details. We do have a distributors at different geographies in Japan, Korea, Taiwan, mainland China, Southeast Asia, in Malaysia, and Singapore, India, Germany, France, Italy, so, and also in Israel. So we have a distributors located. You can always contact them. You can find their contact details on our website, prodigytechno.com. You can also write to us directly, to me, or write to contact@prodigytechno.com. That's an overview of this today's webinar. And over to you, Asif.
Yeah, thank you, Godfrey. Thank you, Vibhav, for a wonderful presentation. I know this is a very hard protocol, and thanks everyone for participating. So I'm opening up for Q&A. So people who have questions can start typing in their questions in the Q&A tab. At the same time, I'm also sending up the feedback form. People can start filling up the feedback as well. So whoever has questions can please type in your questions. Okay. So some of the questions to start with, does the protocol analyzer support UFS 4.0 HS Gear 5?
Yeah, as if this UFS 4.0 supports HS Gear 5A and B. So we support from PWM to HS Gear 5B speeds.
Okay. And is it backward compatible with the lower, because some of the lower specification like 3.1 and below?
Yes, we do support UFS 2.0, 2.1, 3.0, 3.1, and UFS 4.0. All these different DUTs can be tested with the UFS 4.0 protocol analyzer. And if someone needs only UFS 3.0, they can only go for a UFS 3.0 protocol analyzer also, and later on upgrade it to UFS 4.0 as and when required.
We wait for some more questions here. Yeah. So what kind of probing do you support?
We support solder down probes, which you can solder to the test points directly, and we can also guide you while developing these kind of ducts to provide the test points and the test pads. Then we have a mini SMP probe tips which directly connect to the DUT mini SMP connectors, and then we have interposers, as I mentioned, right? Raised platform interposers in the final DUT in the engineering product or a production unit. Someone want to test those products. We also provide a solution for it, and a pre-silicon development platform, which is many times based on FPGA and MPHY chipsets. So we provide a power divider kind of a interposer where you can access the MPHY signals between the host and device, and then take the signals to the protocol analyzer for further analysis. So we have a comprehensive probing solution to address the different needs of the market.
Any more questions people have? You can type in. Or unless people are busy filling up the feedback form, I think it's going to take a while. So yeah, so if you have any specific questions and people who are, okay, there's somebody who's raising a hand. I see that. There's no question. I see a question here, right? Would the recording be sent in case sent as I missed this webinar? Yes, yeah. The session is completely recorded, and if you have participated, if you have registered for the webinar, we will send out the recording to you directly to your email ID. Yeah. So people who are interested in, wanting to know more about the UFS 4.0 protocol analyzer can write to us at contact@prodigytechno.com, and those who want a one-on-one session, or those who are interested in, contacting us directly. So, the email ID is contact@prodigytechno.com. So we would be happy to have a discussion or a one-on-one demo for each one of you guys. So in the meantime, I think, I'm just waiting for some more people to fill up the feedback forms, and if there are any more questions, I would take it. No, I think that's it for now, looks like. So with this, so there's one last question here. Yeah, I think, could you show more details about interposer? So Godfrey, you want to take that?
Yeah, I think it is a very, we have hardly any time left out to show details. I request you to send us an email, and we already talked about different interposers like solder down probe tapes and power dividers, probe tapes with mini SMP connectors, and the raised board interposers. So there are different solutions. So we can definitely, this is an important subject, and we can always contact us for more details.
Okay, so thank you everyone for participation, and please fill in the feedback form, and let us know what is your feedback. And thanks Godfrey and Vibhav and for the wonderful presentation. So with this, I'm signing off.
Thank you everyone.
Thank you, Asif.
Yeah.
Thank you.
Thank you.